Welcome. The topic we'll be discussing in this lecture is maximum likelihood estimation for a normal distribution. So, basically the maximum likelihood estimation actually it differs for different types of distribution. Like we have normal distribution, we have other distributions also. So depending on the nature of the distribution, the maximum we have binomial distribution like that. There are many other distributions available uh, in statistics. So with respect to the type of the distribution, the maximum likelihood estimation differs. So, the most commonly used distribution is normal distribution, and let us try to understand how to estimate the maximum likelihood for a normal distribution. So, this is the objective of this lecture. The normal distribution is represented by this equation: probability of x given the mean mu and the standard deviation sigma is equal to 1 by 2 pi sigma squared e to the power of minus x minus mu square divided by 2 sigma square. So here basically the Greek letter mu represents the mean of the normal distribution. So a normal curve is something like this. I think you are aware of that. This is how a normal distribution curve looks like. Right. So here mu, it's a Greek term. Basically it represents the mean of the distribution. And yeah, so if the if you provide a less value for mu, if you provide a low value for mu, then this curve will shift towards the left. Okay. If you provide a larger value for mu, this curve will move towards the right. So that's what. So basically, mu controls like where the curve should be moved. If you give lesser values if you apply less value for mu, the curve will be shifted towards the left. For larger value of mu, the mean of the distribution, that is, or the curve, so basically the mean of the distribution will be shifted to the right. For lesser value of mu, the mean of the distribution will be shifted to the left. Similarly, the Greek character sigma, it represents the width. It represents the width of the curve, right? So mu represents the mean of the curve, whereas sigma represents the width of the curve. So basically it represents the standard deviation. And so a larger value of sigma, if you provide a larger value of sigma, the curve becomes shorter and wider. So if you provide a very high value for sigma, what will happen? The curve will become something like this. It becomes shorter, but at the same time it becomes wider. Okay. If you provide a lower value of q, if you provide a smaller value of q, the curve becomes taller and narrower. When the sigma value is smaller, the curve becomes taller and also it becomes narrow. Right. So with maximum likelihood, what we are trying to find is we are trying to find the optimal value of mu and sigma, which provides the uh, better, which provides the maximum value for the output. Okay, so that's what we are trying to find. So we are trying to find the optimal value for mu and sigma, which increases the likelihood of occurrence of a particular event. Right. So that's the whole concept. So here, given the data is given the data, we want to find the distribution. So data is given, but we are asked to find the distribution. For this data, what is the correct distribution? That is, what is the correct value of mu and sigma? That's what we are expected to find. So to understand the whole concept, let us start with a very simple case with only one measurement. Okay. So let us assume that this is the weight of mouses, the weight of mouse. Okay. So let us assume there is only one mice. We are taking only one measurement, and the weight of this mice is 32 grams. The weight of this mice is 32 grams, and we are trying to. So now we have only one measurement, and the weight of this mice is 32 grams, and we are trying to represent this through this normal distribution. And for this normal distribution, if you see the mu, that is the mean is somewhere here. So this is what, so probably this is 28. This is 28. Okay. And let us assume at this point the sigma is 2. So mu is 28 and sigma is 2. Now plug into our equation. Now plug into our likelihood equation with mu is equal to 28, sigma equal to 2. But the point, we have only one data point, and that data point measures 32. So just you plug into our normal distribution equation. So 1 by 2 pi sigma squared e to the power x minus mu. So mu is, so in place of mu, we are providing 32. X, our only measurement, that is 32. Okay. And sigma, we are providing 2. So by 2 into 2 square. So if you evaluate this, what you get is 0.03. What you get is 0.03. So that comes at this point in the y-axis, right? But this is a smaller value. We want to identify that value for mu and sigma for which we'll get the highest value. Okay. So we don't know whether this is a small or high or what. So we want to identify. So our objective is to identify the correct value for mu and sigma, which will maximize the output, so that it is called as maximum likelihood. So probably this may not be maximum. So how do we know that? That's what we want to identify, right? Okay. So this is one case. This is just one case. Now let us take another case. Say that now we are moving this curve little towards right. So when you move the curve little towards right, it becomes like this. Now mu is 30. At this point, mu is 30. Let us calculate again. When you calculate for mu equal to 30, sigma equal to 2, and x equal to 32, now we get a value 0.12. It is somewhat better than the previous one, but still we don't know whether this is the maximum possible value or not. So our objective is to maximize the output, and for what value of mu and sigma we'll get the maximum output. That's what we are trying to find. So what should we do? So say for example, if we shift the curve towards left, if you shift the curve towards left, it is if we so now in this case, if you see, the mu comes here. So probably this point is 20, right? The mean is 20. So with mu 20 and with x equal to 32 and sigma equal to 2, if you calculate, the value you are getting is 0.00000, so on, so many zeros and 3. This is too less, right? So here we get a very small likelihood value. Our objective is to get the maximum likelihood value. So what should we do? So basically, to identify the highest likelihood value, what you have to do is you have to plot something like this. For different value of mu, you have to estimate the likelihood. That is, let us say we are starting with mu equal to 20. Mu equal to 20, calculate the likelihood. Okay, I'm calling LH. What is that? Mu is equal to 21, calculate the likelihood. Mu is equal to 22, calculate the likelihood. So on and so forth. Continue up to say mu equal to 50, calculate the likelihood. So like that, if you calculate, you will get different values for, say it goes from 20 to 50. Now you get different values of likelihood value and plot it as a graph. So now when you plot it as a graph, you will get a graph something like this, right? So at one point you will get the peak. So at wherever there is a peak, the slope will be 0, right? So at one point of mu, say for some value of mu, so in this example, for which value of mu you will get peak is basically you will get peak for 32, because we have only one measurement. So if the curve is fitted something like this, then at this point you will get the maximum value, right? Okay. So for one value of mu, you will get the highest uh, peak, and there the slope will be 0. Okay, so we have to identify that point where the slope is 0, because when the slope is 0, only you are going to get the highest likelihood value, and that mu we have to find out. Okay, so this is what we are expected to find. We can identify the peak in the likelihood graph by determining where the slope of the curve is 0, right? I guess you are following. So this graph is plotted for different values of mu, right? We have to apply all the possible values of mu and calculate the likelihood. By this graph, we can identify where we'll get the maximum slope, maximum peak. The maximum peak is represented with slope equal to 0. Okay. So for this given example, we'll get the highest peak for mu equal to 32. obviously, because we have only one data point and that data point weighs 32 grams. So for this, we will get the highest peak, right? Fine. Okay. So, so now it is not only that we have to find mu. We have to, it is not only that we have to find mu, we have to find also. So now we have identified for this data point mu is 32 gram, but we 32, but we also have to find sigma. Okay. So having identified mu, now we can fix mu and now we can fix x and mu. The only one data point is x. So we can fix the value for x and we can fix the value of mu. Similarly, we have to find the value for sigma. Okay. So we have to also find the optimal value of sigma where we are getting the maximum value. Okay. So similarly, we have to do for sigma. For sigma also, we'll give different values and plot the graph, right? So, so for sigma also we have to plot the graph. So for different values of sigma, by fixing the x and mu, we can similarly plot for different values of sigma. And we can plug in different values of sigma to find the one that gives the maximum likelihood, right? So, so when sigma is very small, when sigma is small, we will get something like this. Okay. When sigma is large, the graph, the curve becomes wider and shorter. So you can apply different values of sigma and you can see where you are getting the maximum value. We want maximum. Okay. So uh, we want the sigma to be smaller, as small as possible. Okay. Right. So, so again we have to find that value of sigma where it peaks. So again, at the peak, the slope will be 0. And the maximum likelihood estimate for sigma would be at the peak where the slope of the curve is 0. So whenever we want to identify the maximum likelihood, we have to identify that point in the curve where the slope is 0. Right? Okay. So this is the case for single data point, but this is only for our understanding. But if you see any real world scenario, you will not have just one data point. Obviously, you'll have multiple data points. So when we have multiple data points, how to deal with it? So let us gradually increase. Now let us assume that we have two data points. So we don't have one data points. Now we have two measurement. The measurement of mouse 1 is say x1. The measurement of mouse 2 is say x2. So we have two data points x1 and x2. And now that is represented through this equation. Say let us assume we are assuming initially we are assuming some value of mu. Say we are assuming mu equal to 28 and sigma equal to 2. So with mu equal to 28 and sigma equal to 2, x1 equal to 32 and x2 equal to 34. 2 points. So when you have 2 points, what you have to do? What you have to do is you have to just multiply the two things. That's all. So it is the likelihood of with mu 28 and sigma 2 and with x1 32 into with likelihood of mu 28 sigma 2 and x2 34. So if you fit into this equation again, so this is for two data points. If it is three data points, then again we are assuming, say let us assume initially mu 28 and sigma 2, x1 32, x2 34, x3 30. We are taking 3 points, 30, 32 and 34. Okay. So again we have to multiply all the three. Likelihood of mu 28, this is fixed for all the cases, for x1 32 into for x2 34 into for x3 30. If we have n data points, then the likelihood of mu, likelihood of mu sigma for this value of mu and sigma, the likelihood estimation of x1 x2 up to xn is the likelihood of mu sigma with x1 into likelihood of mu sigma for x2, so on and so forth, the likelihood of mu sigma for xn. So just multiply all these things. So likelihood of mu sigma for x1 is what? 1 by 2 pi sigma squared e to the power minus x1 minus mu the whole squared by 2 sigma squared into so on and so forth, 1 by 2 pi sigma squared e to the power minus xn minus mu the whole squared by 2 sigma square. Right? So if you, when you solve this equation, you can estimate the likelihood of this. We can identify the maximum likelihood for normal distribution. Now, how to solve this equation? Okay. So now that we know how to calculate the likelihood of a normal distribution when we have more than one measurement. So this is the actual logic. So we have to solve this equation. So let's solve for the maximum likelihood estimates for mu and sigma. So what we have to find? We have to find mu and sigma, for which we'll get the maximum estimated value, maximum likelihood value. So how we are going to do? So basically, to get the maximum likelihood, we have to take two derivations. We have to take two derivations. So this is the equation we got, and we have to take to get the maximum likelihood value for mu. We have to differentiate this equation with respect to mu. So one derivative will be with respect to mu, considering sigma as the constant. So when you take derivative for this equation with respect to mu and consider sigma as a constant, you will get the you will get you will get the optimal value for mu, at which we will get the maximum output, right? And the second derivative will be, and for the same equation we have to take one more derivative. This time the derivative will be with respect to sigma, considering mu as a constant. So when you take the second derivative, you will get the optimal value for sigma. Okay, so this is what we are going to do. So we are going to take two derivatives. The first derivative will be with respect to mu, considering sigma as constant. The second derivative will be with respect to sigma, considering mu as constant, right? But actually what we are going to do is, before taking the derivative of this equation directly, we are not going to take the derivative of this equation directly. Rather, we are going to take the derivation of the log of this equation. Why are we doing that? Why not we directly take the derivative of this equation? The reason is, once you take the log of this equation, the equation will become simpler. So so the derivation will become easier. Okay, if you take derivative for this equation directly, the derivation will become more complex. It will become a very big chain rule. But if you take log of this, then it becomes simpler, because when you take log of this, all this multiplication will be converted to plus. For example, log of a into b is nothing but log of a plus log of b, right? The natural log of a into b is nothing but natural log of a plus natural log of b. So we want to apply this formula here, because here it's a multiplication of many terms. So if you apply direct derivation, it becomes complex. So what we are going to do is, we are going to apply, before applying derivation, we are going to take the log of this. So when you take the log of this equation, okay, when you take log of this, so this is log. When you take log of this, uh, so by taking log, the equation does not changes. That's what the slide says. So why we are taking log? One is, our mathematically the equation becomes simpler to take derivative. But by taking derivative, the characteristics of the equation does not change, because the likelihood of the maximum likelihood of the equation before taking log and after taking log will be same for both mu and sigma. Okay, for mu also, this is the peak point of the equation before taking log, and the same thing is the peak point after taking log also. Similarly for sigma also, this is the peak point before taking log, and after taking natural log also, this is the peak point. So the point is, by taking two things, when you take natural logarithm, the characteristics of the equation does not changes, and also the derivation becomes simpler. These are the two reasons why we are taking log. So now when you take log on this, what happens? This entire thing will becomes, instead of multiplication, it becomes plus. Okay. So first let us take one term and see what will happen when you take the log of this. So let us take this term alone, right? 1 by 2 pi sigma squared, so on and so forth. So log of natural log of 1 by 2 pi sigma squared into e to the power minus x1 minus mu the whole square divided by 2 sigma squared. So here are some basic info on natural logarithm. Natural log of 1 is 0. Natural log of e is 1. Natural log of x into y is natural log of x plus natural log of y. Okay. Natural log of x to the power y is y log x. So if anything of this form, a to the power b, and if you take natural log of that, it is b into log of a, right? So all these things will be applying here. Okay. So first, if you see here, this contains two terms. Again, this is one term and this is another term. Both are multiplied. When you apply natural logarithm on this, it will become addition. So log of 1 by 2 pi sigma squared plus this multiplication becomes plus log of e to the power minus x1 minus mu the whole square by 2 sigma square. Okay. Now this square root, see, square root of x can be written as x to the power 1 by 2, right? If it is 1 by square root of x, it can be written as x to the power minus 1 by 2, right? As we are bringing it to the top. The same thing here we are doing. 1 by root of 2 pi sigma square is written as log of 2 pi sigma square to the power of minus 1 by 2. Okay. And this is log of e to the power something. Okay. Already we have discussed log of anything to the power x to the power y can be written as y into log of x. So log of e to the power minus this things is nothing but minus x1 minus mu the whole square divided by 2 sigma square into natural log of e, right? Similarly, the same way here also. So here we are applying log. Now we have applied log. So this, right? Now when you apply log for this is also of the form what? X to the power y. So it will become minus 1 by 2 log of 2 pi sigma square. And here log e is nothing but log of e is 1. So this is nothing but into 1. So this can be ignored, right? And then this is 1 by 2 log of, this is 1 by 2 into log of 2 pi sigma square. Okay. This is minus 1 by 2 minus 1 by 2 into log of 2 pi sigma square. So this can be written like this, minus 1 by 2 log of 2 pi, right, minus 1 by 2 log of sigma square. So basically there are, basically here we have is again it is because of this equation log of xy is nothing but log of x plus y. So 2 pi we are taking a separate term and sigma square we are taking a separate term. So we can separate it out, right? So minus 1 by 2 log of 2 pi minus, basically it's plus. So uh, but there is a minus outer. So when you bring it inside, it will become minus 1 by 2 log of sigma square minus x1 minus with the whole square divided by 2 sigma square. Okay, right. So so log of sigma squared. So this is again this is log of sigma square. So again it is of this form, a to the power b is nothing but b log a. So log of sigma squared is nothing but 2 log sigma. So this becomes minus 2 by 2 log sigma, right? Other terms doesn't change. So this 2 and 2 can get cancelled. So at last we are getting minus 1 by 2 log 2 pi minus natural log of sigma minus x1 minus mu the whole square divided by 2 sigma square. Okay. So this is the term we got for when you apply log on this term for the first term. Similarly, this can be understood for the other terms also. Only thing this, for the second term, this x1 will become x2. For the third term, this x2 will become x3. For the nth term, this will become xn. That's it. So when you plug into this equation, so when you plug into this equation, what you will get something like this. Okay, minus 1 by 2, so on and so forth. You'll get this. Right. Now for this, right. So we get an equation something like this. Okay. So now for this equation, we have to actually take the derivative. So we have to take derivation twice. First, we have to take derivation with respect to mu, keeping sigma as constant, and then we have to take derivation with respect to sigma, keeping mu as constant. Okay. So again, this equation can be still simplified. This term, if you see, this term is appearing for n times. So we can club all these things and we can write minus n by 2 log n 2 pi. So that we got minus n by 2 log n 2 pi. Similarly, this term is also appearing n times. So we can add up all these things and we can say minus n log sigma, right? And apart from that, then you'll have only these terms will be separate for n times. Okay, x1 minus mu minus x2 minus mu by 2 sigma square, so on and so forth, minus xn minus mu the whole square divided by 2 sigma square. Okay, so this is the equation for which we are going to take the derivation, right? So first let us see how can we take derivation for this equation with respect to mu? So it's very simple. So when you take derivation for this equation with respect to mu, if you see this part, it does not contain mu at all. So it becomes 0 when you take derivation. So basically it's a constant. So for the constant, when you take derivation with respect to mu, it becomes 0. Again, for this term also there is no mu. So when you take derivation for this term also it becomes 0. Here we have mu, right? So when you take derivation for this, okay, so when you take derivation for this, what you get is, so let me take this. It is x1 minus mu the whole squared divided by 2 sigma square, right? Minus, this is minus. When you take derivation for this, it becomes 2 into, so minus 2 into x1 minus mu the whole squared into minus 1. Okay, so we are taking derivative with respect to mu. So right, so it's a chain rule. So here you have to apply chain rule. So it becomes this minus 1 also will be multiplying divided by 2 sigma square. Now this 2 and 2 will be get cancelled. This minus into minus, it becomes plus. So there is no sign. So it is x1 minus. So yeah, there is no 2 here. Okay, it is 2 into x1 minus mu into minus 1. So it is x1 minus mu divided by sigma square. That is what we get for the first term. Similarly, we can understand for the second term. It will be x2 minus mu by sigma square, so on and so forth, plus xn minus mu by sigma square. So basically, this is the one. This is the derivation we get when you take derivation for mu by keeping sigma as constant. Now, if you further simplify this, we can take this. We can 1 by sigma square separate out. So you'll get 1 by sigma square into x1 plus x2 up to xn minus n into mu. Right? Let us keep this equation. So this is what you get when you take derivative with respect to mu. Now let us take derivative with respect to sigma, keeping mu as constant. So when you do that, again, if you see this first term, in the first term there is no sigma, so it becomes 0. In this term there is a sigma. So log of x is 1 by x. So when you take derivation of log of x, okay, d by dx of log x is nothing but 1 by x. So derivation of log of sigma is 1 by sigma. So we get minus n by sigma, right? Plus, let us see now this term, how will we take derivation with respect to sigma? x1 minus mu the whole square divided by 2 sigma square minus. For this, we have to take derivation with respect to sigma. So first, before taking derivative, let us simplify this. x1 minus mu the whole squared minus, here it's minus. Let us bring the sigma to the top. So sigma minus sigma to the power minus 2. Okay. So if you, the derivation of x squared is what? Derivation of x squared is 2x, right? Okay. So that is, so that is basically derivation of x to the power n is n to the power n into x to the power n minus 1, n into x to the power n minus 1, right? So now when you take derivation of this, what will you get? So everything is constant. x1 minus mu the whole square divided by 2 is the minus sign is there. This is a constant into minus 2 sigma to the power minus 2 minus 1 is minus 3. Okay. So it is minus 3, right? So that's what we are getting, right? So it is minus 2 into sigma to the power minus 3. Now this minus and minus, it becomes plus. So it cancels. This 2 and 2 also cancels. Now this equation also we can write as x1 minus mu the whole squared. We can bring this down. It becomes sigma to the power 3. So that is how we got this term x1 minus mu the whole squared divided by sigma cube. So this is for x1. Similarly, we'll get for x2. For x2 also we'll get x2 minus mu the whole square divided by sigma cube. So on and so forth. Xn minus mu the whole square divided by sigma cube. Right? So this is the equation we got when we take derivation with respect to sigma. So this also we can ignore this 0. So you'll get something like this, right? And so finally, these are the two equations we get. So this is the one we got when we take derivation with respect to mu, and this is the one we got when we take derivation with respect to sigma. Okay. Now now the story is not yet over. To find the maximum likelihood, you recall the maximum likelihood point appears when the slope is 0. Okay. So we have to equate these two equations to 0. This equation we should equal to 0, and this also we have to equate to 0, and we have to solve this equation for mu, and we have to solve this equation for sigma. That is what we are going to do. Okay. So first let us take this equation and we'll equate to 0. So this equation, when you equate to 0, it is 1 by sigma squared x1 plus so on and so forth up to xn minus n into mu. So when you equate this to 0, you'll get like this, right? So now here what we are doing is we are multiplying by sigma square. When you multiply this equation by sigma square, both left and right side, sigma square into 0 is nothing but 0. Here when you multiply by sigma squared, this sigma squared, this and this will get cancelled, so we get something like this. This nu we can move to the left, so we get nu plus n mu in n mu equal to x1 plus so on up to xn. So mu is nothing but x1 plus x2 plus so on and so forth xn by n. So this is what we get for mu, right? Okay. So now to get mu, so to get the maximum, so for a given data point x1 up to xn under normal distribution, to find the maximum likelihood estimate, the optimal value of mu can be identified by solving this equation x1 plus x2 by plugging the values into this equation x1 plus x2 so on and so forth xn divided by n. Similarly, the second equation should be equated to 0. So when you equate this to 0, you get something like this, right? And here again, what we are doing, so it is 0 equal to minus n. So again here we are multiplying by sigma. So when you multiply sigma into 0, it is 0. Here when you multiply by sigma, this sigma and this sigma will get cancelled. Here when you multiply by sigma, this sigma and this will become square, right? Hence we get this. Hence we get this. Now we can move this n to the left. So you get n is equal to 1 by sigma squared, something like this. Now we can move this sigma square to the left. So we get n sigma square equal to all these things. Now we calculate. So we have to calculate. We have to identify sigma. So sigma square is equal to this. So this entire thing divided by n. Sigma is nothing but the square root of this, right? So this is, so if you want to identify the maximum likelihood value for mu and sigma for a given value of x1 up to xn, right? Just for sigma, for identifying the optimal value for sigma, plug into this equation. For identifying the optimal value for mu, plug into this equation, right? Now for the normal distribution, already we know that as a formula you might have learned from the school days onwards that this is how we calculate mu and this is how we calculate sigma. But how that sigma and mu came, that is basically it is based on this maximum likelihood estimation, right? But this is applicable only for normal distribution. If it is for other distribution like binomial distribution, this style of calculation will vary, but the procedure will be same. Only thing is you have to take a that distributions equation. Okay. So for this value of sigma, you will get the optimal value for which you will get the maximum value, right? So this provides the maximum likelihood estimate of mu, and this provides the maximum likelihood estimate of sigma, right? Fine. So that's it about maximum likelihood estimation for normal distribution. So let us stop here for today's session. Thank you.